So thank you very much, and thank you very much for coming all the talks here. Yeah. So today's plan is the following. So first I explain more about semi-orthogonal decomposition, just a little bit. So for general theory, and then I will explain Boundedness equivalence. So this connects algebra to geometry in some sense. So I will explain this later. And then, so the second section I will explain Vandenberg result. So this shows especially there is saturatedness in the case of smooth projective variety, and so a little bit more, and so in the appendix I will explain more recent result. So that this is my result which is not appeared yet is in the case of some singularity case. But for describing this, I need to use triangulated category of singularities and so on. But I intended to explain so-called triangulated category of singularities, but I did not have time at all. So maybe next year, so I will come here again in the spring, and so I will continue. This is also a very interesting subject. So this is related to so-called matrix factorization and so on. This is very amusing field also. But I will just explain a little bit about this. So this is the plan today. So first, so I'd like to explain some basic equivalence. So suppose that there is a fully faithful functor. So fully faithful, or just B is subcategory of A, and then it is called right admissible. So B is right admissible if and only if F has right adjoint. And it is also left admissible if it has left adjoint. And then, so semi-orthogonal decomposition was, I explained already, but I repeat the definition. So this is like this one. So first condition is that C is equal to B pub, which is nothing but A in A, such that from B A is 0. Yeah. And secondly, there exists for all A in A, there exists distinguished triangle. A goes to C and comes from B like this. So where of course B in there's B in B and C in C. So I said that so this condition is that A is generated by B and C. Okay, so and there's a proposition that the followings are equivalent. The followings are equivalent. The first condition is that B to A is right admissible. And second, A is C B by C equals B part. And third, C is, so C is left admissible. Now these three conditions are equivalent. So it is kind of easy exercise, and so I just explain. So assume the first condition. And so right admissible, so there is right adjoint functor, which is denoted by G, so B. And then I'd like to show second, so second means this condition. So given A, let B equals GA. Yeah. And then, so FGA, so A, there is adjunction morphism like this. So this corresponds to FA to FA, GA to GA. Right adjoint. Sorry, no, this. Sorry. FG A to A. This corresponds to GA to GA. So this is identity map, and if you bring G to here, then you have this map. So this is FA, FA, or FB, and this is also denoted by B. If I consider B as a subcategory, so this is just inclusion. You can always think free faithful functor as inclusion, and then like this, and then by taking the third term distinguished triangle, then I get this triangle. So this is 1 implies 2, and so 2 implies 1 is the following. So suppose you have 2, then so for any A, you have A, C, B. Yeah, and to A you assign B, and so GA is defined to be B. But usually this is not unique, but in this case unique, because so if you have A, C, B, and A, so this is equal C dash, B dash, and suppose C dash and B dash are also in C and B. Then there is, if you take composition, so B to C dash, then because C is on right orthogonal, this is 0. So this is 0. So that means this has some lifting here. Yeah, this has lifting. And also this is unique because so if there are 2 liftings such that coincide here, then there should be like this. So if there are 2 liftings going to the same here, then there is lifting here. But this is 0 always. So this is unique. So in this sense, there exists unique morphism from B to B dash. And also there is unique morphism from B dash to B. And also there is unique morphism from B to B. So this is of course identity. So in this way, there is unique isomorphism between B and B dash. So you have a well-defined functor. So in this way, so you have right adjoint. So 1 and 2 are equivalent. And by changing side, 2 and 3 are equivalent, and so these are all equivalent. So semi-orthogonal decomposition is closely related to the existence of adjoint functor. And so in this relative situation, B is called admissible. So admissible subcategory. And this saturated category means it is, so if for example B is saturated, and when in arbitrary embedding, it is always admissible. So saturatedness implies for any embedding, it is admissible. So that's a very special property, and which I will explain later. Okay, so this is the first remark. So is there any question? No. Okay, so I go on to the Bondar-Ricard equivalence. So Bondar-Ricard theorem. So suppose that X is a projective variety, and E is a locally free sheaf on X. And assume the following conditions. First condition is that this is tilting. So that means home of EP is 0 for all P non-zero. So this is called the tilting condition. And second, generator condition, that is E pub is 0 in dB of coherent X. So there is no right orthogonal object inside in the derived category of coherent sheaves. Then, so let R be the endomorphism ring of E. Then the conclusion is that there exists a functor dB module R to dB of coherent X equivalence. So this is equivalence of derived categories. So there are many versions. So you have also relative version. So X do not need to be an absolutely projective variety, but you have relative projective variety over another space. This is also the same statement and same proof works. So this is quite important because this side is more algebraic. So this R is associative algebra. So in this case, E is locally free sheaf. So R is finitely dimensional associative algebra. So it is purely algebraic thing, and this is finite dimensional. So there is no geometry inside. It's a very simple object, like a quiver algebra, for example, finite quiver generate algebra. So this is not necessarily quiver, but very close, similar thing. And on the other hand, this is more geometry. Yeah. Okay. So, for example, actually, I plan to explain also some non-commutative deformation theory. So, if I want to consider non-commutative deformation on X, it is very geometrically complicated. So, for example, if I have a threefold, smooth threefold, and inside there's rational curve, so P1, and I want to move this P1, and this is geometrically very complicated problem. But if I go to this side, then the structure shift, something like see, maybe we still twist is better, and then this become here very simple object, actually simple object in the module category, and then the deformation is very simple, something like that. So sometimes the complicated problem here is reduced to very simple problem here, so and vice versa. So this is so.
You can find many E, right?
Many, yes, E can be, yeah, many, yes, that's right. So, yeah.
What is the relation between E or if E and E prime?
This is so-called derived monitor equivalence. So if you have another E dash, then dB of mod, not E, but R dash. So, of course, from E dash, you get R dash, endomorphism ring. And this is, and of course, this kind of thing happens in many cases. Even for module category, so this can happen, for example, this is just a field, and this is matrix algebra. They are categorically equivalent. So, of course, this implies this. But this doesn't imply this. So this is much more general. So this has much more symmetry than this. So this is called the derived monitor equivalence. And it is also an interesting subject in the algebra. Okay, so I'd like to explain the proof. The proof is very easy, actually. So proof. So from left to right. So if I have A, so this is bounded complex of left arm module, right arm module. Actually, not D, but first I take just unbounded case, and then what I want is like this. Yeah. So E is right. Sorry. A is okay. This is so E has a left arm module structure because endomorphism ring is R. So in this sense, so F times E. So if F is an R, F times E is just Fe, like this. So there is some left action here. And A has a right action. And I take a derived functor. And if A is bound, even if A is bounded, the result can be unbounded. Because this is derived tensor product. So it is unbounded from below. So it is bounded from above, but not bounded below. And so this is called phi. And there is, so inverse direction is given by the B goes to, so R home EB. So this is inverse direction, but in this case it is bounded. So bounded. So if B is bounded, then the result is also bounded, because this is R home. R home is bounded, so yeah. Now what is the composition of this? Yeah. So I consider, first of all, phi and this is called psi. Psi are adjoint, so home of phi A I think so. Home of A psi B. So this is home of A tensor B. So it is derived. So I should replace this by P. So P is K projective resolution, and B goes to K injective resolution. Then like this, maybe this is I, and so this is home of P and home E I, like this. Yeah, and this is usual isomorphism. So this is adjoint each other, and moreover, if I take the composition, yeah. So if I take phi psi B, so there is adjoint morphism like this, adjunction morphism, and this is nothing but P R and home E and P R E R home. Yes, and it is isomorphic to P tensor R home FF over R, because P is projective resolution, and F, now I have tilting condition, so R home of FF is nothing but R itself. So there is no higher home, and so usual home is just R. So this is P. So this is B. So that means this is isomorphism. So adjunction morphism is isomorphism for this. So if you go from right to left and go back, then this is just isomorphism. So that means from right to left is fully faithful. Yeah. So home B dash is isomorphic to home phi psi B dash, and this is by adjunction, this is psi b dash. Yeah, so psi is free faithful. Okay, so now it is not yet. So no, of course not yet equivalence, even unbounded case. So what I have to prove is that psi is surjective. Yeah. So psi or but I only used the tilting condition, but I use second condition. So E pop is 0. Yeah. So here I use the tilting condition, but now I use second condition, the generator condition. So E pop is 0. So this implies that psi is essentially surjective. So if B is in dB on coherent X, and then if B is not 0, then that implies that R hom E B is non-zero. Now, it's better to put the other way. So if R hom EB is 0, then B is 0. So but this means that psi B is 0. Yeah. So this is free faithful. So the other way may have kernel, but the kernel is 0. So this is equivalence. So now there remains to show the boundedness of the functor. So if phi and psi are both bounded, then I get equivalence of bounded derived categories. But so they are, one of them is already bounded, but the other I don't know. So I need to prove the boundedness of psi. Okay, boundedness. Of psi. Yeah. So how to do this? So I take a stupid. So like this. So suppose B is in dB of coherent X. Now so suppose I start with bounded complex, and then I want to prove that this is also bounded. So suppose that it is not so bounded, then it is bounded to minus infinity. So this part is a part of that. So phi b is like this. Then m is large integer, so like this here, up to here. And so if this is just k minus m minus 1, k minus m minus 2, and so on. So this, suppose this is a complex. Yeah? And then I just cut this here by force. But this is not the correct, or maybe, yeah, maybe I need more sophisticated truncation. So there is two different truncations. Stupid truncation is, this is tau. Tau is t. So real. So honest. Clever truncation. So what is clever truncation? So here this is not itself, but if it is d, then this is just kernel of d. Yeah. This is clever truncation. And then, so then there is morphism of complexes. So from here I have only 0 and 0 and 0. Yeah? And so I need, so this is, I make a little bit more space here. So k minus m minus 1, k minus m. So this is d. K minus m minus 2, and so on. So since I took kernel, this and this are the same. So I have clever truncation. And so there's a morphism like this. And then I take phi of this. Phi to phi psi b, and this is b. So phi and psi are quasi-inverse functors. Yeah. So, but so phi was, sorry, this is something wrong. So I wanted to prove that the phi is bounded. So sorry, this is phi. Sorry, I made mistake. So b is not here, but mod r, and this is actually a, but now it's maybe b. So this is phi, and then phi psi, and this is phi psi. Yeah, like this. But as I said, psi is so bounded. So that means this is bounded above. So b is somewhere here. So b is here, and this is here. So even if this may increase the degree, so this is like this up to here. Yeah. So this may increase the degree, but not sufficiently high to b. Yeah. And so if I take m is sufficiently big, then so I mean degree of psi of tau phi b is so maximum degree. It's strictly smaller than minimal degree of b. So they are separated. And in this case, hom psi tau minus m phi b to b is 0. So in derived category, dB coherent X. So why is this? So in the derived category, B should be replaced by injective resolution. So this part is like this, and B is like this. So this is B, and this is the one, and still a gap here. And B is replaced by injective resolution. So like this. So there is still a gap. So there is no homomorphism of complexes on this. And then so I denote this by H, then that means that psi of H is 0. So H is this morphism. And so psi H is 0, but the psi is equivalence. So that means H is 0 as a morphism. So this morphism is 0. And so, so this morphism is identity at the lower cohomologies. So that means H homology is also 0. That means homology of lower part of the complex is 0. That means phi b is bounded. So phi b looks like infinite complex, but all the complexes below are 0. So that means it is bounded, isomorphic to bounded complex in the derived category. Okay, so this is the proof of the Bondar-Ricard theorem. So I make some remark. So dB of mod R is equivalent to dB of cof X. Yeah. And here inside there is module category, and here there is chief category. And they are different abelian categories in the same derived category, and they are not the same. But this equivalence induces something different, and this is called a perverse chief category. So this is perverse. There was a perfect complex, so very similar notation that this is perverse. So it is called the category of perverse coherent sheaves. Category of perverse coherent sheaves is the category which corresponds to module category by this equivalence. So categorically they are the same, but this category of coherent sheaves and the category of perverse coherent sheaves are different. So they have very similar thing because they are so-called different heart of the same triangle category. So this kind of thing is called the heart. So one heart and different heart, but their nature is very different. So this is very geometric category, and this is very algebraic category. For example, so if you have a point on the projective scheme, then the structure sheaf is a simple object in coherent sheaf. Yeah, so and there are infinitely many. But here, so simple. What is simple object? in Pavas coherency. And this is this corresponds bijectively to simple object in the module category. But since R is finite dimensional, so only finitely many. Yeah. So, for example, if you want to construct a so-called so-called Brillouin stability condition. Yeah. So this is quite important concept, but the existence is quite a mysterious thing. Yeah. But if there are only finitely many simples, then construct stability condition is very easy. So in order to construct stability condition, you need to fix the T structure. Actually, this is determined by the Pavas coherent sheaf and its central charge. And determining central charge is determined by the simples. So you have only finite many simples, and the value is independently. So the value of the central charge is arbitrarily fixed, and then you get Brillouin stability condition. So in this kind of special case, so if you have a tilting generator, then you get stability condition. So of course, this means that the existence of a tilting generator is very special. For example, projective space or something like that. And so stability condition is especially important for Calabi-Yau variety. So Calabi-Yau variety doesn't have a tilting generator. But still locally, maybe it may have a tilting generator, like a relatively Calabi-Yau. Relatively Calabi-Yau case, there are many cases where there is still relative tilting generator. And in this way, you can construct relative stability conditions. Yeah. So this was some remark which is related to other subject. So is there any question? Okay. So now I'd like to explain some application of this. So this is very famous theorem by Beilinson. So let X be n-dimensional projective space, and E is the direct sum of O minus I, where I is from 0 to n. Then this is tilting generator. So in particular, if I put R be the endomorphism of E, then dB of Pn is equivalent to dB of mod R. So this is a very famous Beilinson theorem, which was proved in the late 70s. Maybe 79 or something. So the proof is usually done by so-called resolution of diagonals. Resolution of diagonal. So this is very important, but on the other hand, this resolution of diagonal is a very special property. So, but and also, if you use resolution of diagonal, then you have more precise structure of the derived category. But only to prove this theorem, you don't have to do this. So it's much easier if you use Bondar-Ricard theorem. So the proof is like this. So yeah, anyway, so suppose that there's minus 1, maybe 1, is, so this sheaf is generated by n plus 1. This sheaf has n plus 1 independent sections, and this is surjection. So you can construct a Koszul complex. Koszul complex. So this is O minus 1 to the n plus 1 2, O minus 2, n plus 1 3, and so on up to O minus n. Yeah. And by this exact sequence, if you have already up to here, then you can produce this. So in this way, if you have E, so from E, you can construct O1, and then O2, and so on. And if you use this side, then you can construct minus n minus 1, and so on. So you can construct all OM from E by this kind of exact sequence. And then if you have any complex, so dB of coherent of X, suppose that H may be M of Hn of A is non-zero. So of course, if you take non-zero object, then some cohomology is non-zero. Then you have homomorphism from O minus M for M very large. And then you can extend this homomorphism to hom from OM minus M to A, which is non-zero. So in this way, E is generator. Yeah, of course, this is similar to the resolution of the diagonal, but slightly easier. Yeah, actually, this kind of generator can be constructed in many cases. Sorry. Tilting condition. Yeah, sorry. So this kind of argument works for any projective variety. So in this way, you can always construct a generator like this, but in most cases, they are not tilting. So, but the tilting condition is that P of O of M is 0 for P positive and M is minus M to M N. So like in this range. And this is true for projective space. So the point is the vanishing theorem. Yeah, so this range is very strict. So if you go one higher or one lower, I think you don't have vanishing anymore. Higher is okay, but lower. So yeah, that means hn of O minus n minus 1 is k. So yeah, this is residue homomorphism. So it is very strict. Okay, this was the Bondar something theorem. Now I'd like to explain the saturated category. So what is saturated category? So first I define. So let T be a triangulated category, and so this is called home finite. If for arbitrary A and B in T, summation of dimension of home A, B, M is finite. So for all M. So it says not only home set is finite, but all the shift included is finite. So this for the home finite condition. And next definition is from H from T or T opposite to the category of abelian groups is called cohomological functor. If this is contravariant, and so this sends distinguished triangle to long exact sequence. So this is a cohomological functor. Yeah, and it is also called finite type if a summation of dimension of H of A M is finite for M. And for example, suppose that T is home finite category, and A is arbitrary object, and then HA is HA of B is home BA. So this is representable functor. So this is cohomological and finite type. If the category of home finite. So this by definition. Yeah, and I give you one example of home finiteness. So suppose R is this finite dimensional algebra. So this is two-dimensional commutative algebra, and this is not home finite. So because if you take K as R module, then it has projective resolution so multiply x and x, and so these are all two-dimensional vector spaces, and this is one-dimensional. So this is projective resolution of K. So home KK M is a K for all M. So it is not home finite, home infinity, home infinite. So by using the same thing, so I get question. So K is not a compact object. So one can prove this by using the same exact sequence. So K is a very, very small thing, so, but it is not compact. Yeah. So some geometric idea doesn't work well. So in algebra. Okay. So now I'd like to explain the theorem. Is there any question? So the theorem. So this is originally Bondar-Kaplanov theorem, but it is there was some error, so it is Bondar-Vandenberg theorem. So the statement is the following. So suppose X is a projective variety, and let F from perfect X to mod K be a cohomological functor. Yeah. And then it is representable. F is F A for some A in dB of mod X, coh X. So here I didn't assume that X is smooth. So in this case, derived category of coherent sheaves and perfect complexes are different. But any cohomological functor from perfect complexes is represented by derived category of coherent sheaves. So the difference is called triangular category of singularities, and this is important for the singularity theorem. But I do not talk about this time.
Just a silly thing. So when you say a projective variety, you mean the X is reduced actually. Both X is reduced.
Actually, this is not necessary, I think. Yeah.
This dual number is then the projective variety. Then does it cause some problems here?
No. So perfect complex is. So this one is perfect complex, but this one is not perfect. Yeah.
But basically, K can be replaced by perfect complex.
Perfect complex should be bounded, but this is unbounded.
Yeah, that's right.
Yeah.
So it is only perfect complex.
Yeah. So it is not necessary variety. Projective scheme is sufficient, I think. Yeah. So there's a corollary. If X is smooth projective, then X is saturated. That means if dB of X is contained in some triangular category, then it is always admissible. Right and left admissible. Right admissible and left admissible. Sorry, if it is home finite. Home finite on dpx. Yeah, so this is not a very nice expression. And the proof is like this. So if you have any A, then what I need is that the representable functor from a something is home finite, where this maybe b, for b inside dbx. So I don't need any home is home finite. So only what I need is only b is inside dbx. And then by the theorem, so this functor is fa. So fa. So fa is represented by fa dash, where a dash is in db of x. So that in this way, I have a right adjoint functor from t to dbx. Adjoint functor as before. Yeah. So in this way, I have always right adjoint functor. But the left, how about the left adjoint? So this is done by using cell functor. So for smooth projective variety, I have a cell functor, but the cell functor is closely related to canonical divisor k, and so this is very important in the birational geometry, but maybe I don't have time to explain this. So just, yeah. So this kind of close connection to k is explained a lot in my survey paper in the differential geometry. Okay, now I'd like to proceed to the proof of Bondar-Vandenberg-Bondar-Kaplanov theorem. So proof. So this is again an application of yeah. Okay, so application of Brown representability. So why is this? So this is just a finite category. So they cannot apply Brown representability directly. So I need to go to quasi-coherent sheaf and so on. So somehow I have to extend first and then go back to the finiteness. That's it. So sorry. Okay, let's continue. Now, so there is a duality functor from mod k to mod k defined by vector space is sent to dual vector space. So this is a contravariant functor. And if you restrict this to module, this is infinite dimensional vector space, and this is finite dimensional vector space. So if you restrict this to the finite dimensional vector space, then this is involution. But for the infinite dimensional vector space, it is not involution. And then so I have given so I'm given f already. F is from perfect x to mod K, and then I compose this with D, so this is perfect to mod K, and then I extend this to G tilde from, so this is actually G. G is extended to G tilde from D Q co X to mod K by so-called Kan extension. Kan extension. KAN extension. So defined by following. So G tilde A is colimit of C to A of G C. So arbitrary element in this big derived category is a colimit of compact object. So C is compact. So nothing but perfect F. And A is covered by compact object, so infinitely many compact object. And so A is covered by a lot of compact objects, C dash and so on. And then gluing this, you get the colimit of this. So this is Kan extension. So this is in mod K. Yeah, now this preserve coproduct. So G tilde preserve coproduct, because coproduct is nothing but direct sum. So by Brown representability, so there exists E inside DQ co, such that G tilde is nothing but FE, represented by E. Yeah. So then if I go back to D again, so D of FE restricted to D of dB of coherent X. So FE was G tilde, and so if I restrict to here, then this is G, just G, and the G was DF. So this is nothing but DDF, and this is F. So what does this mean? This means that F of A, for A is in the dB, is equal to hom of E AE. So now so F, the original functor, is represented by E, which is unbounded complex of quasi-coherent sheaf. So what's remaining to show is that this E is in dB of coherent. So remain to prove is that E is inside dB of coherent X. Yeah. So this is the first step. The first step is Kern extension and Brown representability. So this is straightforward. But the second step is more difficult. So how to prove that this representative object is actually coherent and bounded? So,
Do you mean E is quasi-isoquic to an object is derived?
yes, that's right. Yeah, thank you.
Just was it quick?
Yeah. So, I mean, inside this, yeah. So this is, anyway. So, now, embed X to projective space, because X is projective scheme. So this is P. And then, so I draw diagram. So dB of perfect X to mod K. So this was F. And then, so there is dB of Pn. So this is P star. So pull back. So dB, Pn is smooth. So this is the same as perfect complex. So you can pull back and then perfect complex. And then there is equivalence dB of R. So this is varies on equivalence. So denoted by phi. And the composition is denoted by F dash. Yeah. So and F is represented by F is Fe. So E is in D of Q co X. So how about the F dash? F dash is represented by something. So F dash of something, so maybe A, is nothing but so F P star phi A. Yeah. And so this is represented by so E P star phi A and E, and this is equal to hom of phi star phi A and P lower star E. So P upper star and P lower star is adjoint in this way. So this is right adjoint. And this is hom of A and psi P star E. Yeah. And suppose that the A is R itself. Then, so this one is nothing but psi. So F dash R is equal to like this. R psi P star E, and this is just psi P star E as a complex. Or maybe this is not complex, so this is maybe I should take H0. Yeah. So, of course, if I take Hn, then this is H minus n. Now, what is F dash Rn? Anyway, F dash sent this to finite dimensional vector space and also bounded. So, home finite. So this is home finite. So this is also home finite. So since F is home finite type, that means that F dash Rn, so the dimension and summation is high. And that implies that psi p star E is in dB of mod R. And if you, so that means P star E is in dB of Koch Pn, hence E is also in dB of Koch X. So this is the end of the proof. So I used, in the latter part, I used Beilinson theorem. So this Beilinson theorem is used always in this way. So this is very explicit theorem, but you can use also this kind of very general result. So projective space is something, a mother of everything. So everything can be embedded into projective space. So in this way, so everything in algebraic geometry is reduced to the some calculation on the polynomial ring. Of course, definition is from polynomial ring. So that's like this. So now time is over. So I just state what I proved. Now is the following. So X is projective variety, and suppose E is a locally free sheaf, and suppose L is a maximal Kawamata sheaf, so that means if it is n-dimensional, then depth at the cross point is n at cross point. Something like this. So actually this F is obtained from L by non-commutative deformation. So let R is endomorphism of E, and assume the following conditions. First, E is flat over R. So this is related to non-commutative deformation. And it is also tilting. So home EE is 0. P. EP is 0 for P non-zero. And 3, L generate D singular X. So this is the quotient category of dB by perfect complexes. And this is all. And then, so dB of mod R, there is some free faithful functor to T inside dB of Koch X. So T is the image, and dBx has semi-orthogonal decomposition like this, and T pop is in perfect complex, and this is saturated. So this T pop is saturated. So what is the meaning of this? So in the if X is smooth, then right, so it is saturated. So already the whole category is saturated. But if there is singularity, then it is not saturated. So there is some bad thing, so related to singularity. And so this is the so-called category of singularities. This is the difference between the whole bounded complex to perfect complex. And the assumption that this Koyama-Kore sheaf has all the information along the singularity. And then sometimes by non-commutative deformation, you get locally free sheaf. So that is perfect complex. So this is not perfect, but by deforming, you get perfect complex. And then, so this is the deformation algebra. So it is flat over this. And also this is maybe tilting. Then this T is not the whole category, because this E doesn't generate the whole category. Because E is E generates T. So T is the part where E generates. So phi is defined in the same way as, so phi of A is A times E as before. So in this way, T is the part generated by F and E. So maybe this is not a whole derived category, but if you take the semi-orthogonal complement, then the complement doesn't touch the singularity, because E already contains all the information on the singularity. So this is contained in the perfect category perfect complex in saturated. So it is a kind of smooth part. So the remaining part is as if it is smooth. For example, if you have a weighted projective space, then this has semi-orthogonal decomposition like this, dB of kx divided by x cubed, and maybe square, and the dB of kx divided by x cubed, and dB. Okay, something like this. Of course, if you have a more complicated case, you have more complicated thing. But so this part is generated by O of -2, -3. And this part is generated by O -2. So this is L dash maybe. In this case, it is slightly more complicated by this, but because it has more singularity. But so you can modify the statement for more L and L dash, and then like this. And the remaining part is this. So this is the part. So this kind of decomposition is possible. So decomposition is that smooth part and singular part. So this decompose by using non-commutative deformation. So this is the theorem. I originally intended to explain, but this time the lectures concentrated on more general topic, which I think. But this general topic is maybe more interesting in some sense. It doesn't use any specific geometry, but but on the other hand, it uses a lot of technique coming from algebra, so like Brown representability, or Kern extension, and so on. So maybe next year I will talk about more geometric things. Yeah. Thank you very much for this.